All right, let's go over the quiz. So again, this quiz was harder, trying to get you prepared for the gateway exam. First gateway has pretty similar problems to this. So you want to make sure you can do this kind of thing. And yeah, don't worry about the variable name, just differentiate with respect to that variable. In the first problem, that's t. On the gateway, you might be given just something like this. And you need to realize that when you take, say, the fourth root of something, that is the same as the 1/4 power. And that means you need the power rule in conjunction with the chain rule. dy dt, the derivative, you need to think about taking the derivative of something to the 1/4 power. So you bring down the 1/4 and you raise it to the 1/4 minus 1 power, which would be negative 3/4. The thing you raise to that power is whatever's inside the parentheses. 2t cubed minus 5t squared plus 3t. 1/4 minus 1 again is negative 3/4. Times, the chain rule says, do an extra step, multiply by the derivative of the inside function. So the derivative of the inside function there, you must use parentheses, is 6t squared minus 10t plus 3. Those parentheses are absolutely necessary. If you didn't put a dot there, but you did put parentheses, I will assume you meant multiplication. That will be okay. But the parentheses are a must. You're multiplying by that entire thing. You don't put it there. If you don't put parentheses there, it's as if you're multiplying this only by the 6t squared. But no, you're multiplying by the entire thing, the entire derivative of the inside function. Second problem, you need the quotient rule plus the chain rule, along with memorized derivatives of cosine and natural log. Low d high, derivative of cosine of 3x by the chain rule would be negative sine of 3x times 3. Now, it's understood that this is cosine of 3x. I didn't put parentheses there, but that would be understood. If you maybe put the 3 over here and didn't have parentheses there, it would be okay. But if you put the 3 there, you really should have parentheses around the 3x. That's why I always, as a default, when I'm writing this, put parentheses. I was copying this from pieces of old gateway problems, and that didn't have it in there. So you should realize it really is parentheses there. So low d high minus high cosine of 3x. D low, the derivative of 7 is 0. The derivative of negative natural log of 4x would be negative 1 over 4x times 4. As long as you put the dots there, it's okay. You can also put parentheses around this if you want. But the dots would need to be there at least, or the parentheses at least, to indicate that you're multiplying here. The 4's do cancel. The minus signs do cancel, but you don't have to simplify. And in fact, I'm recommending not simplifying, so you don't make mistakes in your simplification. Over the square of what's below, 7 minus natural log of 4x, quantity squared. Okay, make sure you stop me if you've got a question. I know a lot of people have been having difficulty with these quizzes. So I'm sure there might still be questions. Please stop me if you have a question here. And don't be embarrassed about it. It's okay. You're not the only one that might be struggling. Question 11?
Yeah, so number 2, I simplified it to positive cos 3x over.
Yeah, that's fine. Negative signs cancel. You can put the x down there, yeah. As long as it's in the top of the fraction. G prime of y. If you've memorized your derivatives here, this is the easiest one, perhaps, or maybe number 4. Derivative of arctangent, which is the same as derivative of inverse tangent, is 1 over 1 plus the variable squared. The variable is called y here, so it's 1 over 1 plus y squared. And the derivative of inverse sine or arc sine is 1 over square root of 1 minus y squared. So those are just memorized. By the way, that does mean something about integrals here. It does mean, for example, the integral of 1 over 1 plus y squared dy would be arctangent of y plus c. You're not being quizzed on integrals, but that could come up on exam 2, which I believe is 2 weeks from today. Integrals like this could come up. And it would also mean the integral of 1 over square root of 1 minus y squared is arc sine of y plus c, or inverse sine if you prefer. Those are the same thing. Derivative of secant is secant times tangent, but we have a 7x in there, so we need the chain rule as well. We need to ultimately multiply times the derivative of 7x, which gives you an extra factor of 7, which you could just put out in front. But don't forget to also plug in the inside function. You need 7x's inside the secant and the tangent arguments as well, not just x's. And the last one, maybe the trickiest one, you're going to need the fact that the derivative of tangent is secant squared. You'll need the chain rule and the quotient rule because you got a quotient inside there. This quotient is the inside function for the chain rule. The chain rule says take the derivative of the outside function, which is the tangent function, to get secant squared. But then plug in the inside function, 2x plus 1 over 3x minus 1, but then multiply times the derivative of that inside function. It's always the same. I'm saying the exact same things over and over again. You've got to think about these kinds of things over and over again if you're going to remember them. But the inside is a quotient. I need the quotient rule. Low d high minus high d low over the square of what's below. Could simplify the top here, but you don't have to, and I'd recommend not bothering for the purposes of quizzes and gateways. Any other questions at all? Not for the gateway, no. For exam 2 you will, but not for the gateway. As I said at the beginning of the semester, factual knowledge is certainly not the end all be all, right? Higher order thinking skills, the catchphrase goes, are more important. Problem solving skills are more important. But I claim, and I think the science backs me up on this, you can't have good higher order thinking skills, good critical problem solving skills, unless you know some things, okay? So even though you may forget a lot of these things to some degree after this class is over, or maybe even after the gateway, it's still worth the time and effort to put some effort into trying to remember things. If nothing else, it helps you remember kind of the way something might go and might help you look something up if you need to. If you don't know anything, then you won't even know what to look up. So knowledge is important. Your mind needs something to wrap its mind around if you're going to be able to apply what you're learning. It's just like, reading, you can't read for comprehension if you can't actually read for the mechanics of it. And it is very much analogous to learning anything, a sport, musical instrument. You got to practice. There's just no way around it. Okay, for 99.999% of people, including me, you've got to practice if you're going to get better. And practice in the right way. Learn how to practice. All right. So we got 37 minutes here left today. I do want to come back to implicit differentiation and partial derivatives like we were talking about on Friday, but I think it'd be good to do some other things first. First thing I want to mention is a general rule for differentiating inverse functions. You remember when we derive the derivatives of natural log of x and arctangent of x and arcsine of x, that we use the fact, for example, sine of arcsine of x always equals x for, well, at least all x's in the domain of arcsine. In general, when you got a function and its inverse function, assuming the inverse function exists, you can write this kind of equation. F of f inverse of x gives you x, gives you the original input, at least for all x in the domain of f inverse, whatever that happens to be. I'm not specifying. When f is invertible, it's got an inverse function, f inverse. So there's lots of background assumptions going on here. I'm assuming f is invertible. It's 1-to-1. It passes the horizontal line test. No horizontal line goes through its graph more than once. So I'm assuming F inverse exists, and I'm also about to assume it's nice, it's differentiable. Assuming, well, both F and F inverse are differentiable, meaning they have derivatives everywhere, I can differentiate both sides of this with respect to x. Apply the d dx operator. The right side's simple, it differentiates to 1. What about the left side? Well, you don't know what f and f inverse are, so you cannot actually figure out a formula, but you can, well, at least an explicit one, though you can figure out an abstract formula based on the chain rule. You have an inside function and an outside function. F inverse is inside, f itself is outside. The chain rule says take the derivative of the outside function, plug in the inside function, then multiply times the derivative of the inside function. I guess we'd have to write that like this. F inverse quantity prime of x. This is something you should be able to derive on the test if I asked you to, what I'm showing you right now. It's abstract, but it's a kind of abstraction that if you've learned the chain rule well enough, you should be able to handle. That's the derivative of the outside function because f is the outside. Plug in the inside function because f inverse of x is the inside function. Multiply times the derivative of the inverse function. There's a natural kind of symbol to use for it. What's my goal? My goal is to solve for the derivative of the inverse function. So now, assuming this is non-zero, if this is non-zero, I can divide both sides by it, and I get the derivative of the inverse function evaluated at a number x is the reciprocal of the derivative of the original function evaluated at f inverse of x. F prime, 1 over f prime of f inverse of x. And there's a general formula for the derivative of an inverse function. Does this have any applications? Plenty. For one thing, you could apply this to derive the derivatives of natural log of x, arcsine of x, and arctangent of x, though we've already done that. You also can apply it to find derivatives of functions, some functions in some cases where maybe you even can't find a formula for the function. For example, suppose f of x is x cubed plus 2x plus 1. I claim, first of all, that that function is invertible. How do I know that? Well, I know what its graph looks like. I could graph it on my calculator, but I can also think about it. I've had enough experience with this to know its graph looks about like this. It is a cubic. It's actually always increasing. It does have what's called a point of inflection right around here. Y-intercept is 1. Actually, I'm not positive that that point of inflection is above the horizontal axis. It could be below it. I'm not sure. I also can plug numbers in here to graph it. And for example, I could plug in 1 and get an output of f of 1. 1 cubed plus 2 times 1 plus 1 is 4. That's the output of f when x equals 1. Being a graph like this, it passes the horizontal line test. No horizontal line goes through it more than once, which means it has an inverse function. And if you wanted to graph the inverse function, you could graph the line y equals x and try to reflect it across that line, which is, again, tricky to do. Maybe turning your paper like this would help. The inverse function, trying to imagine reflecting this red graph across this green line. Well, over here, it's going to look something like that. And then in here, it's going to look something a bit tricky here. Something about like this. Now, I'll turn it back this way. That's the graph of y equal to f inverse of x, approximately. Do I know a formula for it? No, I don't. Is it possible to find a formula for it? Technically it is, you can solve cubics, though the answer is really, really complicated. And I'm not going to bother. Can I find a derivative of this? Well, it depends. It depends on what input you're thinking about. I claim for the input 4, it's easy to find the derivative. When x is 4 for f inverse, what is y? You should be able to answer that. Go ahead and say it. 1. Why? Because f of 1 is 4. They undo each other. F of 4 is 1, is right about there. But what is the derivative of this function at 4? What's the slope of the tangent line? Use this formula that we just derived. F inverse prime of 4 by this formula would be 1 over f prime of f inverse of 4. Careful what things are primes and what things are negative ones, representing inverse functions. That's 1 over f prime of 1. The reciprocal of the slope of the red graph at x equals 1. That kind of makes some intuitive sense. This slope here is, I don't know, maybe about 2 or 3 or so. This slope here looks like it's maybe 1/2 or 1/3 or so. To finish the problem, I do need to find f prime. F prime of x here is 3x squared plus 6. Yeah, that's f prime of x, 3x squared plus 2, sorry, plus 2. F prime of 1, therefore, would be 3 times 1 squared plus 2 is 5. The slope of this red line is actually 5. Right, no mistakes there, that look good. That means the slope of this purple line here is 1/5. The answer is 1/5. So the slope of this tangent line to this purple graph. Even though you don't know a formula for f inverse, you can still find that particular slope. Doesn't mean all the slopes are easy to find, because there are other values of x, it's not so clear what the output would be. But for this example, since I know f of 1 is 4, I know f inverse of 4 is 1, and I can actually figure it out. Okay, you should be able to do this for homework due Wednesday and maybe the exam in 2 weeks. So make sure you think about it for other examples as well. Next thing I want to do is very, very briefly mention the derivatives of 2 functions called hyperbolic functions. Hyperbolic cosine and hyperbolic sine. You do not need to know these derivatives for the gateway, but I do want to mention these things because they do sometimes come up in applications, especially if you're in physics or engineering. Sometimes you run into hyperbolic sine and hyperbolic cosine. What in the world? Sinh of x and what, cosh of x? Yeah, these are honest to goodness functions that maybe you've heard of and maybe you haven't. Probably most likely you haven't heard of these before. The hyperbolic sine is defined to be e to the x minus e to the negative x over 2, which is the same as 1/2 e to the x minus 1/2 e to the negative x. And the hyperbolic cosine is defined to be e to the x plus e to the negative x over 2. 1/2 e to the x plus 1/2 e to the negative x. Why do we call these hyperbolic sine and hyperbolic cosine when obviously they are exponential functions? Well, it's because they kind of act similar to trig functions. The derivative of hyperbolic sine, sinh of x for short, is, well, to differentiate this thing, you're going to get 1/2 e to the x minus 1/2 e to the negative x. Then because of the chain rule, another factor of -1 comes up there, right? When you differentiate that, derivative of negative x is -1. And then this simplifies amazingly, to hyperbolic cosine. Isn't that cool? Just like the derivative of sine is cosine, the derivative of hyperbolic sine is hyperbolic cosine. Huh, weird. What about the derivative of hyperbolic cosine? Got to differentiate this thing here. Once again, I need the chain rule for the second one, and I get an extra factor of -1 again. And because of that, I get this, which is, lo and behold, hyperbolic sine. The analogy isn't perfect. The derivative of sine of x is cosine of x. The derivative of cosine of x is negative sine of x, right? Well, it's almost completely analogous. The derivative of hyperbolic sine or sinh is hyperbolic cosine. The derivative of hyperbolic cosine is hyperbolic sine, not negative of hyperbolic sine. But it's still kind of similar. There's also a hyperbolic tangent and a hyperbolic secant and a hyperbolic cosecant and a hyperbolic cotangent that can be defined. But we won't bother. That's about all I'm going to say about these functions. You don't need to know them for the gateway. If I tell you what they are on exam 2, you should be able to certainly differentiate them to check this if I asked you to. And I'm not ruling that out, but they won't be on the gateway. They do come up in applications of physics and engineering sometimes, including to what are called partial differential equations. And if you ever learn about complex numbers, there's another deep reason why these act similar to sine and cosine. They are actually related to the sine and cosine functions when you allow the input numbers to be imaginary or complex numbers. If you don't know about imaginary numbers, it's okay. I'm just hinting at it to you. Kind of a wild thing. All right, that's all I wanted to say about section 3.8. I'm not going to give you any homework problems on it, but if it interests you, you can certainly study it. Next thing I want to do is talk about section 3.9, introduce section 3.9 for about 10-15 minutes. Then we're going to go back to implicit functions and multivariable calculus and maybe Mathematica again. Maybe not Mathematica today. Somebody could email me right now. I still did want to email that file from last Friday to you, but I kept forgetting. If you could just actually, we better pick somebody. Can somebody raise their hand and say volunteer? Well, okay. Email me, remind me to send you last Friday's Mathematica notebook with the contour plot in it. Sure, right now, yep. So this is section 3.9. We've actually been doing section 3.9 for quite a while without telling you that we've been doing it. The title is called Linear Approximations, and the derivative, I'll just write linear approximations. We've been doing this actually since chapter 2, when you talk about the derivative as a rate of change. You know, if the velocity, for example, is at instantaneous velocity is 5 meters per second, and you travel for another 0.1 units of time, or 0.1 seconds, you'd multiply 5 times 0.1 to get 0.5 as your approximate change in distance traveled. That kind of approximation we've been talking about since chapter 2. Now we make it a bit more formal, you might say, in section 3.9. We're given a quote-unquote nice function, call it y equals f of x. This must be somebody crashing our Zoom. Assassin indeed. Is that you? Okay. Okay, all right. Okay. Given a nice function, y equals f of x, define near some particular value of x. Call it x equals a. What does nice mean? Certainly continuous and certainly differentiable. And actually, if I assume it's differentiable, it would automatically be continuous. I don't know if you remember, but 4 weeks ago or so, I did say that if a function has a derivative, it's automatically continuous. One way a function can fail to be differentiable is it can fail to be continuous. You can have a jump discontinuity. Goal: approximate f of x for x near a. In other words, for x approximately equal to a. These are vague words. What does it mean to say x is approximately equal to a? Like, is it within 0.1 units or 0.01 units? We purposely leave it vague. Maybe we'll try to get a little bit more precise on Wednesday, but not today. How? Method. Use a tangent line approximation. Use a tangent line approximation. Think about a graph here. Let's say the graph of f looks like this. Let's say a is right here. So this point has coordinates a comma f of a. The tangent line to the graph at this point would look about like this. Tangent line. It's got a slope equal to f prime of a, right? That's maybe an exam question everybody should definitely get right. The slope of the tangent line at this point would be f prime of a. That's what the derivative tells you. If you don't get that, you're not really getting calculus at all. Okay? That's what derivatives tell you. What's the equation of that tangent line? If we want to use the tangent line to approximate the function, we probably should have its equation. Well, let's think about the, how about the point slope form, where you do y minus a y coordinate of a point you know equals the slope m, or, well, the slope is f prime of a times x minus the x coordinate of a point you know. What point do we know? This point. We're pretending, for the sake of argument, we know what a is and we know what f of a is. So subtract f of a here. That's just some number. It's the y coordinate of this point here, second coordinate. And here we subtract a. Hey, I can solve that for y as a function of x by adding f of a to both sides. And if a is fixed, so that that's some fixed number, like just pretend it's, I don't know, -1. And this is some fixed number that we could pretend is, say, 1/3. And this is some fixed number like 7 or something. Then this would be a function of x. I could also multiply the f prime of a through the parentheses and try to simplify it to slope-intercept form. But I don't have to. And in fact, it's better, typically, when you're doing this kind of thing, to leave it like this. And as far as an approximation goes, the tangent line is very close to the graph of the function. So I can say f of x is approximately this expression, the right-hand side of the equation of the tangent line, f of a plus f prime of a times x minus a, when x is close to a. X is approximately a. That's called a linear approximation. Linear approximation. I'm using a line, the tangent line, to approximate the function f. Do you have to use the tangent line? I mean, couldn't I draw other lines in here that are pretty good approximations to f? You could, but certainly the tangent line is the best one to use. It most closely matches the curve near a. If you zoom in to that point closer and closer, the purple and green lines will look more and more alike. That's the idea of local linearity, differentiability, we talked about in chapter 2. This is way more useful than you might imagine, okay? Now, it doesn't feel so useful here in the age of calculators and computers, because why don't you just plug things into your calculator? You know, why do we need to approximate it with some formula? Well, Historically, people didn't have calculators and computers when they first were talking about calculus, first figuring this stuff out. And so, yes, it was certainly useful computation tool back then, 1600s, 1700s, 1800s, and the first half of the 1900s. But hey, with calculators and computers, is this still useful? I claim it still is. For one thing, it emphasizes the meaning of calculus, which helps you understand calculus better, which helps you apply it better. And for another thing, these approximations are good for more than just numerical computations. They're good for other things besides, including learning how to solve differential equations, for example, which if you're an engineering major, you'll need to know. And even if you're a chemistry major, you might need to know, like in physical chemistry, you do some basics with differential equations. If you're a biology major, do you need to know it? Well, it depends on what subject you specialize in, but certainly sometimes in biology, you need to know calculus when you're talking about rates of growth of a population, for example, or maybe rates of a tumor growth, if you're not talking about populations. There are lots of things, even in biology, where differential equations are helpful, and this can help you understand and indeed even solve differential equations better. But we do it for more mundane things here in Calculus 1. You can't do the advanced stuff unless you can do the basic stuff. Let's use it for a mundane thing. Let's approximate, oh, how about square root of 4.1 without a calculator. Ha ha ha, without a calculator. Just to emphasize that it can be done. Well, obviously the answer should be close to 2. So isn't that all I would need to do? Well, no, we want to go a little bit beyond that. We want to go beyond saying it's approximately 2. We want a little bit better approximation. So I should probably say, using calculus. In other words, a linear approximation. How? What in the world? What should I do here? What's my function? That's not so clear. Well, it becomes clear when you think about what you're doing. We're taking the square root of 4.1. Maybe my function should be the square root function. I'm really trying to approximate f of 4.1 if f of x is the square root of x. So that relates it to a function, a differentiable function when x is positive, that we can try to find a tangent line for. What do you think I should use for my a, though? 0? My a on the other sheet, here it was just an arbitrary number, but maybe I should pick something specific. You got a guess as to what I should use for a? That's a good first guess, and I'm glad you guessed it. Problem is, if we're going to use f of 4.1, we would be needing to use the thing we're trying to estimate. But hey, square root of 4 is simple. That's just 2, right? Maybe I should use a equals 4. And yeah, that is the best thing to do. 4.1 is just a little bit bigger than 4. Think of it as 4 plus 0.1. Use that as the a, since I know the square root of 4 exactly. That's a good thing to use for a. I need to find f prime of x if I'm going to use the linear approximation. Use the power rule, 1/2 x to the negative 1/2, which is the same as 1 over 2 times the square root of x. A is 4. I need to find f of 4 and f prime of 4. F of 4 is square root of 4 is exactly 2. F prime of 4 is 1 over 2 square root of 4, which is 1 over 2 times 2, which is 1 over 4, or 0.25. Now use these things. Use that linear approximation. 3 dots means therefore. Therefore, f of 4.1 is approximately use this formula here with a equal to 4. It's approximately f of 4 plus f prime of 4 times x minus 4. The a is 4. I'm using 4 again because these are nice and simple numbers. So this simplifies to 2 plus 0.25. I should replace x with 4.1 here. Times 4.1 minus 4, which is 0.1. And yeah, I can do this in my head. This is 2 plus, move the decimal to the right one spot, the left one spot to get an extra 0.025. 2.025 is my guess, my linear approximation to the square root of 4.1. It's approximately the square root of 4.1. Square root of 4.1. Yep, close to 2.025. This approximation, you can see when you compare it with the calculator, is a little bit too big. What's the reason it's too big? Anybody got a guess as to the reason it's too big? And by reason, I mean in a picture. Why do you think this linear approximation is slightly too large? Based on the picture I'm starting to draw. And continuing to draw. And continuing to draw. What is it about that picture that tells you you're going to get an answer that's a bit too big? Go ahead. Yep, exactly. And that means the line is above the graph. We're trying to approximate the second coordinate on this graph when the first coordinate is 4.1. The second coordinate at that point is the true value of square root of 4.1, which is going to be an irrational number. What we just did in finding this value is finding the second coordinate on the green graph, the tangent line. That point has coordinates 4.1, comma 2.025. But because the red graph is concave down, its slope is decreasing. Its tangent line's got to be above it. So the green line over approximates the true answer. We get an answer slightly too big of the more true answer. The more accurate answer, I should say. Even this is not exactly right because the calculator is still approximating, but it's closer. So that would be an example of a basic kind of use of linear approximation, and you should be able to use that for the homework due Wednesday and the exam in 2 weeks. All right, the last 8 minutes of class here. Let's see if we can finish another implicit differentiation problem. And if we have time related to multivariable calculus, somebody put something in the chat here. Okay, somebody's looking for a group. So Millie's looking for a group if you know her. Sorry if you didn't want that shared. I didn't know that was what it was going to be here. By the way, if you are somebody else who needs a group, well, you could work with Millie, or I can help you try to find groups, but I need to know who needs help finding a group, so send me a message. What I'd like to do is look at problem number 23 in section 3.7, this one right here. Find the slope of the tangent to the curve that you see here, sine of x, y equals x, at the point x is 1, y is pi over 2. Sine of x, y equals x at the point 1 comma pi over 2. So that would be x equals 1, y equals pi over 2. Find the derivative. Find dy dx. You could actually solve this for y as a function of x, You could take the inverse sine of both sides. To get xy is the inverse sine of x, and then divide both sides by x. Though there might be a question about differentiability. There even may be a question about differentiability here as well. I'm not positive how this is going to come out. Could end up being undefined possibly, but there's no hint of that. So what you need to do is you need to pretend y is a function of x. Assume y is a function of x. Now you could go ahead and replace the y with an f of x like we did last Friday, but you don't have to. And in fact, that's not the standard way to do it. Instead, you just go ahead and you differentiate this. Apply the ddx operator, you might say. And in your mind, remember, y is not a constant here. It's a function of x. I'm making that assumption. So the derivative of sine is cosine. So you get a cosine, but I need the chain rule too. I need to plug in the inside function, then multiply times the derivative of the inside function. Well, and the right-hand side differentiates to 1. See how that works? I'm using the chain rule there. The outside function is the sine function. The inside function is x times y, where y is some function which you could give a name to, like f of x, but I'm not bothering to write the f of x. However, now I'm not done. I need to differentiate that. That's a product of two functions. I need the product rule. And yes, y is not a constant here. It's a function of x. So the derivative of the first function, x, is 1 times the second function, plus the first function times the derivative of the second. The derivative of y with respect to x is not 0, because y depends on x. You're making that assumption at least. By the way, we're not positive that that assumption is valid near this point, but we're not worrying about it. So the answer is dy dx. Now solve this equation for dy dx. Divide both sides by the cosine function. Get y plus x dy dx equals the 1 over the cosine of xy, which you can also write as the secant of xy, if you like, but you don't have to. Then subtract 1 and divide everything by x. So yeah, you could write the answer as secant of xy minus y all divided by x. That's one way to write the answer. And it does look like we're not dividing by 0 when we plug in this point here. So there's, yeah, evidently no problem with differentiability. So now I plug in the point dy dx at the point 1 pi over 2 is secant of 1 times pi over 2, which is secant of pi over 2, minus pi over 2 all over 1. Secant is the same as 1 over cosine. Oh, and here we do run into trouble. Excuse me. This is undefined because cosine of pi over 2 is 0. So my initial hunch that it might be undefined is correct, and we actually can't finish this problem, or they want you to find that it's undefined. Essentially, the graph has an infinite slope there, but at least the mechanics you should be able to do. I wasn't expecting that problem to happen that way when I first thought about doing it, but it did. 2 minutes. How is this related to multivariable calculus? What should you be able to do with this related to multivariable calculus? Well, this equation does have some graph. I'm not bothering to graph it today. Some set of points that satisfies it. I have no idea what it looks like. That graph would be a level curve of a function of two variables that I could form by subtracting x from both sides. And I'm not really setting this equal to 0. I'm just saying it's a function of x and y. And you should be able to find partial derivatives of this thing. If you call the output, say, z, and treat now x and y as independent variables. Don't treat y as a function of x here. That, again, might seem contradictory, but again, it's all in your head. Whether something is a constant or a variable is all in how you're thinking about it. And here I was thinking about y as depending on x. Again, it actually was not valid because we got undefined, but it might be valid at some other points. Here, I'm not thinking that way. I'm thinking of x and y as being independent variables. You should be able to find the derivative of z with respect to x. Treat the y as a constant now, not as a function of x. Differentiate this sine to get a cosine. Use the chain rule now to differentiate that with respect to x. I get an extra factor of y, not the product rule. I'm not going to get the same thing I got here. And then differentiate x, you get -1. I could also differentiate with respect to y, treating the x as a constant. I get cosine of xy times x, plus -0. And I could find second order partials, etc. Let me just say here in 10 seconds that on Wednesday, we will talk about how to interpret these things. And the best way to interpret it is, well, two ways, graphically and with linear approximations. So it's going to tie into section 3.9, which we were talking about 15 minutes ago. Okay, so we'll come back to it and talk about it more on Wednesday. See you then.